In this lab, we will be exploring Newton's second law and the role it plays in predicting an object's motion. This includes the use of two equations. Final velocity equals initial velocity plus the net force divided by the mass multiplied by the change in time. Also, we can use final position equals initial position plus the velocity times the change in time. Specifically, we will be looking into the concept of an object moving at a constant velocity and how this results from a net force equal to zero. We will then be able to compare the motion predicted by the use of Newton's second law with the motion of the object in real life and compare our findings. In this video, I captured a golf ball rolling across a level surface at a constant velocity. I set my coordinate system all the way over to the right so that the first frame of motion is set at the origin, as the golf ball then moves along the x-axis in the negative x direction. If I were to flip the x and y axes though, this would change only the direction of the ball's velocity and its position. It would not change the magnitude of the ball's velocity though. Since velocity is a vector, and this means its components are both magnitude and direction, the ball would therefore have a different velocity if the axes were to be switched. Over to the right, we have a position versus time graph of the golf ball, and then this data is presented in a table in the bottom right, which we can then use to calculate the average velocity, specifically using the initial time and the final time, as well as the initial position and the final position. Using the equation velocity equals change in position over change in time, we can input the values found in Tracker, including the final position, the initial position, the final time, and the initial time. Using this, we can then find the average velocity to be negative 0.61 meters per second. We can then input this into the Python code to predict the object's motion. We can then input initial conditions of the ball's motion into the code. First, I set the ball's mass equal to 0.045 kilograms. I then set its initial position vector as it appears here, with the x-coordinate being negative 0.044 meters. We can then set the initial velocity of the ball using the previously calculated value from the equation velocity equals change in position over change in time. We can then go down to the motion prediction section, where we set the F net vector equal to 0 since there is no net force acting on the ball and it is moving at a constant velocity. While the ball is moving at a constant velocity and therefore has a net force equal to 0, this does not necessarily mean that there are no forces acting on the ball, but rather that all the forces acting on the ball cancel out. While we know that the normal force and gravity are two of the forces to cancel out, we cannot be sure of the other forces acting on the ball. We must then manipulate Newton's second law so that the code can utilize it to predict the motion of the ball. Here, we can predict final velocity of the ball by adding the initial velocity to F net divided by mass and multiplied by delta t. Since F net is equal to 0 here, this further shows how the initial and final velocities are the same. Next, we can predict the ball's position by adding the initial position of the ball to the velocity of the ball multiplied by change in time. Once we input this information into the code, we can then run the code to get a model of the ball's motion. Over to the left, we have a model of the golf ball's actual motion as it moves from right to left along the x-axis. Over to the right, we have a position versus time graph of the ball's motion, which shows how it moves at a constant velocity in the negative x direction. After running this code, we can then use the position and time data that we obtained from our experiment in Tracker and compare this with the data that we obtained from the code for the model. Once we input all of the data into a graph, we can then compare the experimental data, which is the blue dots, with the model data, which is the red line, and we can see how they both follow the same general trend. Towards the middle of the graph, the experimental data differs slightly from the model data, perhaps due to uncalled for outside forces such as friction. Overall, though, they both follow the same general trend line. In conclusion, both the experimental data and the model data provided an accurate representation of the use of Newton's second law to portray the motion of an object at a constant velocity.